Okay, so starting this live stream, and I just need to check if everything's working correctly, so just give me one moment. Okay, so just as I had feared, the name of the live stream is under the last live stream, but this is the chemistry live stream, even though it says human geography. So please just give me one moment. Okay, so sorry about that pause. If you're behind and you just joined like 10-15 minutes later, it's okay. You could just skip to the current stage if you want, or you could just listen along. Let me just apologize in advance for my voice. I got attacked by pollen of grass and my allergies started acting up, so apologies for that, and I might have to blow my nose. So just warning in advance. So unlike last time, I'm going to try to go over things that you need to be able to understand rather than just restating stuff that's on the chip. So that being said, you should, if you watch this live stream and ask questions and such, you should look over your chips to just know that recall information that's going to be present in the fill in the blanks on the test. So with that being said, I'm just going to go over these labs really quickly. And also, if anybody has any questions, even if it's not related to what I'm going over at the time, please ask it. That's the whole point. Like I said, almost all, I'm pretty sure all of this information is on the chips. And I'd rather have the focus be answering your questions. So just going to get into it. So firstly, water has calories lab. That was way back when, long time ago. And we got a couple of beakers, or two beakers with different amounts of water. And we saw that the beaker with less water started to steam up first. So the temperature was higher, even though it had the same, it was exposed to the hot plate for the same amount of time. So we also learned that water can hold energy, which we call calories or joules that we learned later. And the energy required to heat 1 gram of water by 1 degree Celsius is 1 calorie. Wonderful. Okay, somebody has a question. If David has a question, please say your question in the chat. Thank you. Also, I'll be checking the chat about every 5 to 10 minutes. And also there is a delay, so if you ask a question and it's not acknowledged right away, please don't fret. Just wait a couple of moments and I will read it. So, anyways, when you mix two different, okay, let's say the water from two of these different beakers, or water with different temperatures, when you mix it, they reach equilibrium temperature, and which means like an intermediate temperature. So it doesn't just depend on how like which temperatures of the water is. It depends on how much of each type of water there is. Okay, so the question that David asked is, I'll write this off to the side. Wow, that's not supposed to happen. Okay. So, question. You just type it up. Yeah, like I said in the very beginning, I know it's the wrong name. I really don't know how to fix it. Please tell me how to fix it. Thank you. So the question, meanwhile, is the energy required to heat, I'm assuming one, it doesn't say one, but 1 gram of water, 1 degree Celsius, considered big calorie or just calorie? And the answer is small calorie. It's just one small calorie. Okay. So that's that for water has calories. It was a really simple lab. All we did was get 2 beakers and put them on a hot plate. It looks like this, but without the third beaker. So the next thing we did is hot shots. So we experimentally found the specific heat of a metal that we didn't know before by using this formula, which is change in heat in calories equals mass times specific heat times change in temperature. So we did that by finding the energy that was given to the metal by the water, by using the water's change in temperature and all the information that we already knew about water. So we got the calories that the water gave to the metal, and we made it equal to the metal mass times the metal's change in temperature, and we solved for the specific heat. And I'm going to check the chat. So okay. So I'm going to try to fix the name. So just give me a couple of moments for that. Okay, I don't think I can change the name at this point. I'm so sorry. But, oh, the name changed by itself. Okay, thanks whoever did that. So, another chemistry-related question. Thank you. The question is, do we need to know water has calories and hot shots for this BE? I don't think it's on the beep. Okay, the reason why I included it was because it kind of is just kind of to make sure that you understood these concepts, because the same type of concepts, like using the equations from these labs, were in labs like finding the heat of fusion of water. So don't stress too much, because as was pointed out, it's not on the beep. So it's just to make sure, maybe just jog your memory of things that you already know. So, melting icebergs lab, what we did was we found the energy needed to heat ice so that it melted into water. And this is connected to the heating curve, because it depends, like you use this heating curve to figure out how much energy you need to get from one point to another. So really, it's like a journey, I guess you could think of it. Like if you're at negative 25 and you have ice, and you want to get to, let's say, 50 degrees water, there's like 3 steps you have to go to. You have to heat the ice to 0 degrees. That's what's called ready to melt. So it's just 0 degrees ice. And you have to actually melt it, which is this line right here. And while you're melting it, the temperature doesn't go up. Like all the energy that you expose to the ice is just used for melting it and not raising the temperature. So that's the second step. Third step is going from 0 degrees water to 50 degrees water. which we all know it's it's just with this formula. So the way we used the way we used this equation to find how much energy you needed to melt ice is we found the energy that was given by the warm water that we put in before we put in the ice. So we assumed that whatever the warm water gave to the ice is what the ice received. So that means like heat wasn't lost to the surroundings. So when the ice was absorbing this heat, it had to do two things. It melted to like 0 degree cool water, melted ice, and then it kept heating up, so it kept receiving more energy even after it had melted. So that's why you have to subtract the energy. So if you want to find energy used to melt, you need to find the energy used to heat up the melted water after it melted and subtract it from the energy given by the warm water. So I will check the chat. Okay. Shivam Kumar wants a shout out. There you go. Okay. Wow, there's 2 people watching. All right. So continuing on to more current things. So Goblet of Fire, we observed 3 different types of fuels burning. We saw candle wax or paraffin in the candle. That was in the little metal dish. And we saw rubbing alcohol. We dropped 19 drops in a little metal dish, and we saw it burn. And we also saw butane in liquid form in the lighter. Okay, so I'm going to check the chat, see it again. Okay, so David On, you're the real one. Thanks for asking all these questions. So, what was dissolved in, I'll just write it down somewhere. What was dissolved in water to make an endothermic reaction in the ice pack? And somebody else has already answered it. It is urea. Okay. And I will double check to make sure there weren't any other possible answers. Right, it was urea. And you could also refer to the chip. Urea itself wasn't on the chip, but all the other types of things you can mix to make cold or hot packs. Okay, so we have another question. What is urea? We didn't go that much into it, but I can look that up for you. I'm pretty sure it's related to, let's see, it's apparently excreted in urine. That's why the word urea sounds like urine. Apparently. Okay, so, but you don't have to know. That's just a fun fact. Okay, so, what we learned from the Goblet of Fire was when, okay, we have another question. Well, this is good. Question, like the emphasis on questions. How do you make a hot pack reusable? Okay, so the hot packs that we studied, how do you make a hot pack reusable? So the exothermic reaction in the reusable hot pack was crystallization of a certain substance. And the reason why you can make it reusable is that if you make it uncrystallized, I don't know the technical term, but after it's crystallized, it's been releasing heat. Great. But if you want to make it go back into like the non-releasing heat form, you make it uncrystallized, and you do that by, in the example that we saw in class, you do that by putting it in water that is hotter than the heating pack. So then the crystals kind of, they like seem to disappear. So then it's not giving off heat. So the reason why that hot pack was reusable that we saw in class was that the exothermic reaction was the crystallization. Okay, so we learned from the goblet, and we continue on. Great question. Keep going with the questions. The reason why we learned that fuels need oxygen to combust and produce water and carbon dioxide was when we lit the alcohol on fire and put an upside down beaker over it. And we observed that the fire went out. Okay, and showing that it needs oxygen. Like, I don't know, if you're messing around with a candle around your house, then you put the lid on it and then the flame goes out. So it obviously needs oxygen. And the water condensed on the sides of the beaker that we put over the candle, the alcohol, and showing that the combustion reaction produces water. So that's what happened in Goblet of Fire. So going on to paraffin power. So what we basically had was a candle under an aluminum can. Aluminum can had some water in it. And the water was intentionally below room temperature to minimize loss of heat to the surroundings. And and the aluminum can was held up by this sort of metal stick and a clamp. So we found out how much heat was released by the paraffin candle burning by measuring how much heat was absorbed by the water that was being heated up. And we assumed that it was equal, even though we know the efficiency was not 100%. So the reason why the paraffin didn't burn at 100% efficiency specifically was airflow. In the room there's vents, so there's air moving around taking heat away. And also the flame itself, because it's producing carbon dioxide and taking in oxygen, that creates a little bit of a current, so to speak. So that's why. And when you're asked for efficiency, you have to divide the actual calories per gram that you got out of the candle, and you divide that by the theoretical, right? So for paraffin, that would be around 1 big calorie, I believe, and 10 big calories. I misspoke. So you have to divide actual by theoretical. Just remember that. And then you get a decimal, which is like the percent efficiency. So it's like you're using that much percent out of its potential. So in the lab, we also saw some black substance on the bottom of the can, which is called soot, like the stuff in a fireplace. And this is because of incomplete combustion, which is why, which occurs because the flame doesn't get enough oxygen. So instead of producing carbon dioxide and water, like exactly like we saw in most of our equations, it produces soot and carbon monoxide, which is very bad and can suffocate you. And we also expanded on that in your body as like an engine, because your body also does an oxidation, I think that's the wrong word, but it has glucose and oxygen react to produce carbon dioxide, water, and energy that you use for your bodily functions. We learned this last year in 9th grade. And okay, I will check the chat. What was Nehemiah's bagel story trying to explain? Okay, so that was the intro to Unit 4, the flyer. And I think it was intentionally, it's an introduction, right? So we don't have to know I'm pretty sure we don't have to know the technicalities yet, but I think it was something to do with how neon acts. But like I said, as far as the intro goes, we're probably only going to need to know quote-unquote trivial things for the fill-in. So I would just focus on knowing what was in the intro, and just don't stress too much about trying to understand every little detail, because that's intentional, right? Because it's like an intro, which we're going to continue on after winter break. Right, so the cellular respiration that I was talking about is exothermic, which means it releases energy, and photosynthesis is the opposite, so it's endothermic, absorbs energy. And then lastly, the last lab is the heat from nowhere. So we worked with different salts, and some produced energy when they dissolved, and some absorbed energy. So they were endothermic or exothermic depending on the salt. And we also talked about like different types of reactions. So endo, exo, what does it all mean? So an endothermic reaction absorbs energy from the environment, right? So that's why if we touched a beaker that had an endothermic reaction going on, it would feel cold to us because it's absorbing energy from our hand. So because of that, it's kind of kind of confuse me when we're talking about how much heat was produced slash absorbed, because in an endothermic reaction, if you write out heat as a reactant, or not a reactant, I'm sorry, if you write it into the reaction, it will have a positive. Okay, I misspoke yet again. Okay, so we have more questions, and I'll focus on that first. So, can I verbally explain the top part of chip 61, day 59, where it shows Hess's law using A, B, and C? So, yes, I can. Chip 61. Okay, so basically, Hess's law, we can go to that right now, actually. You're given intermediate equations to try to find out the heat produced or absorbed in like a final equation, so the goal equation. And you can do different types of operations, so to speak, like in math. So you could flip, which is you write the reactants as the product and the products as reactants, and you change the sign of the heat that's written off to the side. You could divide, so if you have coefficients on each one, you can divide, but you also have to divide the heat by the same number, or you can multiply. And basically what it's saying is, it's kind of like linear systems of equations from Algebra 1, is you're trying to cancel out what you don't need and place reactants or products to where you do need it to get to the final equation. So on day 59, chip 61, the top of it, it says, I'll take this out actually, A plus 2B, and it will yield 55 kilojoules equals AB. So the letters just represent random substances. The substance doesn't really matter, it's just as long as you know that you're looking for certain substances and some substances you don't need. So you try to cancel those out, the ones that aren't included in the goal equation. So this basically, it's just a way to try to translate Hess's law into math that we're familiar with. And if you don't get this with the equal sign, it's okay, because that's not Hess's law. It's just a way to try to explain it to you. But you could think of this as the arrow, or like the yield sign in a chemical equation. And basically what you have to do is, if you were dealing with a linear system of equations, what you would do is add it at this side of the equation, add this side of the equation to this side of the equation, and you'd add this side to this side. So what you would get if you did add everything, then, like, I'm not doing any operations right now, I'm just writing it all together. And the purpose of this is to illustrate that you can cancel out things on the opposite sides of the yield sign. So plus C. Okay, then we have AB subscript 2 plus AB plus BC plus KG. Okay, and if you were to simplify this, look, so the whole point of this is to know that on the opposite side of whatever sign, so here's the equal sign, but Hess's law is supposed to be like a yield sign. So you just, if you were trying to simplify this equation, you would just subtract what you have on both sides, right? So if this is on both sides, we can just subtract both sides by negative AB2. And then essentially it's just gone, right? And same thing here. If you want to talk about how much energy is produced, you could just subtract. Right, so that's what the equations are trying to explain. And it's just trying to relate something that you already know from Algebra 1 to Hess's law, which really is if you have substances that you don't need that aren't in your goal equation, you're supposed to, you have to cancel them. And the way you cancel them is by having them on opposite sides of the yield sign. Okay. If you still have any further questions, please ask. I think it did that justice. So we have another question. Are both photosynthesis and cellular respiration endothermic? No. Okay. So I will go back to that section. So cellular respiration and photosynthesis are opposites. So photosynthesis has energy as one of its products. It absorbs energy and it stores it. So it's endothermic because it's taking energy from the environment. Whereas cellular respiration, it's the like literally the opposite if you write out the equation. So instead of the energy being on the left side as a product, like in photosynthesis, the energy is on the right side as a... Oh, I just realized I misspoke. Okay, again. Instead of having the energy as a reactant on the left side of the equation, like in photosynthesis, for cellular respiration, the energy is a product on the right side of the yield sign. So cellular respiration is exothermic because it has energy as a product. Okay. I will continue on. It doesn't seem like there's any other questions. Let me check to be sure. Right, okay. So it doesn't seem like there's any questions, so I'm going to keep going on. Again, if there's any questions, please feel free to ask. Even if it's not related to what I'm going over, please ask any questions. Okay, so we established heat from nowhere, cold/hot packs. I'm supposed to say hot. Okay, they use different ingredients such as urea and water, like we discussed previously. The other types are on the chip. This is the one we did in class, cold pack. So, example time. Hess's law was introduced at the end of the chapter, so if you're not used to it, I think practice is the best way to go, and there's lots of practice problems available online, but here's one. So what the goal is to find the heat. Why did we keep doing that? Okay, the heat produced or absorbed of this equation. Okay, and I got this from outside of our learning materials, so if you don't recognize the substance, it's okay, it's totally fine. I'm going to check the chat again. Okay, will you go to formal me? Yes, Emma. I've been waiting a long time for you to ask that. Anyways, in period 7's last ME, fats release about blank 0 kg per gram. Okay, so I will pull that up. So the question, fats release about blank 0 kg, I think, kg per gram, a little bit less than paraffin. So I believe, let me double check to be absolutely sure, but just 1 second. Okay, so we were given okay, so fats. So in class, he's told us sugar and fat, 4 and 9 big calories. So calories per gram. Okay, so we were given big calories, so all you have to do is convert this 9 calories. And he mentioned today that you can memorize this by remembering the 49ers. I don't know if that helps you. So you have 9 big calories. Just imagine that's over 1, okay? 1. And then you just do units. So we know. So we know 1 big calorie equals. So here it says 4,184 joules. So that's just 4.84 kJ. And then you'd go ahead and find that. Okay. So doesn't seem like there's any questions. So we're gonna go on to Hess's law. Oh yeah, it's gonna be so fun. Okay, so we're gonna find, this is our goal equation. Okay, so we're trying to get here eventually. So this is what we're given. So we have 2 of these and some oxygen, but we know that there's no oxygen right here, so we're gonna have to figure out how to get rid of that somehow. And then we have some CO2. There's no CO2 here, so we're gonna have to figure out how to get rid of that. And then H2O, same for that. We have to figure out how to get rid of it, but we will. Just persevere. Okay, so right off the bat, we only have 1 of this, so we're gonna half this. Okay, so I'll do 2 over 2, 3 over 2, 2 over 2, 4 over 2. You don't have to do the fractions like this, but for me, it helps me keep track of like what I have done so far. So that helps me, but if it doesn't help you, please don't do that. Okay, so just like we divided everything by 2, we also have to do that to the heat. So we did that. So like a check mark, I don't know how to put it in a check mark, but I'll just put in a smiley face. We did that. Okay. Now we have the third one. So we need H as a product, but here it's a reactant. So what we got to do is we got to flip it. That's the first part. So I'm just going to do some cut and pasting magic here. Okay, equation flipped. And since we also flipped the equation, we have to change the sign of the heat. So instead of releasing this many kilojoules, it's absorbing because it's the opposite reaction. Great. So now the second part of this step is halving. The reason why we half it is that we have 2 H's, we only need 1. So 2 over 2, 2 over 2, and then we assume this is 1, so 1 over 2, and then we have to also half the energy. So yeah. Okay, so that's done. Now, last thing. So we have, we also need this to be a product, but it's reactant. So same exact thing. Same exact thing, just flip it. So list the products as reactants, and then reactants as products, and then you flip the sign on the heat. Okay, there we go. Okay, so that's good. So then we change the sign here. Okay, so now let's just double check. So we have 1 of these. Great. We have 1 of these. Great. We have 1 of these. Great. Now we have all this extra stuff. We have the O2s and we got the CO2s. So let's look at this. So we have 3 over 1.5 O2s. Then we have 1.5 O2s. Wow, it's so perfect. Okay, so since these are both on the same side, since this O2 and this half O2, they're both listed as products, okay? So you can just imagine in your head, like, okay, so on the product side, we've got 1.5 O2s. And on this side, we have 1.5 O2s. Wow, it's brilliant. Okay, so we could go ahead and, let's see, how do you do strike through? Strike through, okay. cancel that out. Amazing. Whoa, whoa, whoa. No, 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 no. Okay. Strike through. Okay. Option shift 5. I'll remember that. Okay. Option. Okay, great. Now we've got CO2 to worry about. So we have one CO2 as a product and one CO2 as a reactant. It's so perfect. Okay, so we just cancel it out because they're on opposite sides. So one CO2 is listed as a product. The other CO2, one CO2, is listed as a reactant. So we just cancel that out and it's amazing. So, and canceling doesn't have any effect on the heats. So cancel, I forgot to put CO2s. Amazing. Okay, so, and then you do all these operations, you add it all up, and you get this. It's great. Okay, so I'm going to check the chat. Also from period 7's ME, the most dangerous E blank, M blank, R blank category. What are the blanks? Okay, so, okay, the blanks would be, because they're talking about wavelengths, so that kind of gives you a hint. Where should I write this? Okay. Sorry for any background noise. By the way, my family is a really animated bunch, so okay, you know what, we'll just put it here. But there we go. I like that font. Okay, so period 7. Okay, the most dangerous E blank and blank R. Oops, spoiler alert. Okay, so right afterwards it talks about radiation lengths, so that just gives me a hint. It's like electromagnetic radiation. So that's that. Think this is gonna wrap it up. That's all I had to go over. If anybody wants any more in-depth explanations, please do not hesitate to ask a question. I know that I didn't go too much into heating curve of water. Okay. So, is the Hess's law problem, example problem, answer rounded because I got 85.5? Yes, it's rounded. I think I'm good. I think you guys are good. The 6 people watching right now. Thank you. That's like 4 more people than last time. If nobody's got any more questions, I think I'm going to wrap it up. Good luck to everybody watching. Make sure you go over your chips to get that. Okay, so there's a question. Yes. Do I have any advice for memorizing the lab procedures? Okay, so personally for me, what I do is I just read the chips to like make sure I understand the lab procedures. And I know it sounds weird. I just imagine doing the lab. I don't know why, but that just helps me, like the melting iceberg lab. So like, okay, first you get the cup and then you measure this and then you measure this. So that helps me. Also, what helps other people is just testing themselves. So just read every lab, make sure you understand like what's each thing you do, and just cover it up, or like don't look at the chip, don't read off it obviously, and just try to quiz yourself. So like, okay, so first in this lab you do this first, and then you measure this. That's something that really helps me. Okay, for some reason the chat is disconnected. Okay. So that's my advice for memorizing the lab procedures. If you know yourself to not be that kind of learner, like where you don't learn well that way, don't follow what I say. But just if you like know, like you learn best for like quizzing yourself, that's definitely something that I would recommend. Other than that, I think I'm going to wrap it up. Don't see any other questions. And thank you all for watching again. And any feedback also would be very appreciated. I try to shift away from just restating what was on the chip this time and actually like focusing on understanding stuff that might be a little harder to understand. Other than that, read the chips, get decent amount of sleep, and you got it. Okay, I think I'm gonna wrap that up. Any last calls? Any last clever anecdotes? I don't know. Stories that anybody wants to share? Okay. Okay, so I think I'm going to interpret that as everybody being done. All right, thank you guys for watching again. I'll work even harder. I'm also probably going to do like a big comp review for those of you that have to take the huge exam. Yeah, so it's just going to be like a party, study party. So that's all for today. Thank you. May you have good day tomorrow. May everything go your way, and I'm going to end that now. So thank you.